our challenge here is to discretise in space the heat partial differential equation. The u by dt is d squared u dx squared, as perhaps the simplest partial differential equation that we're going to solve numerically. We're going to approximate this differential equation on the interval x between 0 and 1. We're going to provide boundary conditions that u at x is 0 is 0, just for example, and that u at x is equal to 1 is, say, sine 8t. And we're also going to supply some initial conditions saying that at time t is 0, u field will have some distribution, say 6x into 1 minus x, a nice parabola. Right, now the first thing is to draw a picture. There's the x-axis, that's the space. We're interested in the domain 0 to 1. And to discretise this PDE, we recognise that the error in this discretisation is going to be proportional to h, where h is the distance between grid points and is used to estimate the second derivative. So let's divide this interval into a set of equi-spaced intervals of size h. Now this means that there are now n points along here. The leftmost point we'll call x1, that's 0, and the rightmost point is xn, which is 1, and then x2 will be this point, and that has coordinate h, x3 is 2h, x4 is 3h, and so on, all the way up to xn minus 1 is n minus 2 times h. Now, since there's n minus 1 intervals, we know that h is, in this case, 1 over n minus 1 in order to go from 0 to 1. So what that means, for example, is these x grid points are defined to be xj is j minus 1 times h. Now, what we're going to do is keep track of the value of the field u at each of these points. So a key variable that we're going to deal with is u at the jth point. That's u evaluated at xj, and that will be a function of time. And we're going to find differential equations for its evolution in time for each of these. Now, two of these we know already, and that's very important, and that is, by the boundary conditions, we know that u1 of t, which is u of x1 of t, which is u of 0 t, from the given boundary conditions, that's 0. In a similar manner, the other one that we know is un, because that's u at the value x, grid point xn, and xn is our rightmost point, x is equal to 1, and the boundary condition is that that's going to be this given function sine of 8t. So that tells us what u1 and un are. What about the values of u at all of these other grid points in between? We find them out from the partial differential equation. So and we find them out as a differential equation. So let's consider duj dt for j between 2 and n minus 1. Right, duj dt, so that is du by dt at xjt. From the differential equation, du by dt is the second derivative with respect to x. That's uxx evaluated at xjt. And now discretisation is an approximation, and it is the approximation of replacing this second derivative by its discretisation. So that'll be 1 over h squared into u of xj minus ht minus 2u xjt plus u xj plus ht. Running out of space there. Now let's have a look at the quantities here. We've got 1 over h squared, u of xj minus h. Suppose we're at the jth point here, xj. Xj minus h is a distance h to the left, and that's the grid point to the left, xj minus 1. So this is u at xj minus 1t minus 2u of xjt plus u of xj plus h. Now, if you're at xj and you move a distance h to the right, you get to the next grid point, which is xj plus 1. So we've got a name, that's x, u of xj plus 1t. But now we've got new names for these. The new names are that u evaluated at grid points are uj. So this is 1 over h squared into u j minus 1 minus 2uj plus uj plus 1. And that is duj dt. Right, and that's a differential equation for the evolution of uj in terms of the neighbouring values of uj, and that's valid for j in the interior, 2, 3, all the way up to n minus 1. So that's the n minus 2 interior points, and plus these two values on the boundary. And we're going to integrate this with computationally. But to solve this, we need some initial conditions as well, and they come from the initial conditions here. So directly from this initial condition, we can say the initial value of uj times 0 is u at xj 0 from our definition here. And u of xj0 from this formula is 6 xj 1 minus xj. So that gives a value for the initial values of all of these interior points and an initial value for that set of differential equations. And we'll solve those computationally.